Today's tutorial is about binary search tree. The previous data structures that you already know about them are a bit different with BSD. We had array, we had linked list, we had queue, stack. For all of them, when we wanted to search an element, or when we want to find an element at the middle or at the end of the stack or queue or linked list, we need to go through all the elements. And in the worst case, only for insertion, we were okay, because for insertion, immediately at the end of a stack, queue, or linked list, we can add a new element. But when we want to modify or when we want to search for a specific element, we needed to go, in the worst case, we need to go to pass all the elements. And it was very time consuming. For example, when we have 100 million people, when we have the data for 100 million people, and we want to find one person, maybe we need to go through 60, 70 million record, and after that we can find the specific one. So we want to reduce the time of searching element and time for modifying element, time for searching element, and time for insertion of element is not reduced in this data structure, but because other thing will optimize. So totally BSD is a good structure in terms of time. But in terms of memory, we need some amount of memory to keep BSD. So the memory that we need for BSD is considerable. Here we want to create a BSD with this element: 50, 30, 25, 71, 80, 99. How we do it? We start from the first one. We start from the first element, 50. Then we put it as root. After that, we look at the next one. In BSD, always the left child keeps the smaller one, and the right side, the right child, keep the bigger element. So what about the equal one? Equal one goes to left side or goes to right child? Now I'm asking you. For example, if after 50 we have another 50, it goes to left child or right child? Yes, correct. So left. For less or equal elements, we go to left child. We put it in the left child. And for the bigger element, we put them in the right child. Okay, so 30 is less than 50, so we put it at the left. 25 is less than 30. Always we check the main roots and the child roots. So 25 is less than 30, so we put it here at the left of 30. Then we have 71. So we check the main root. When we check the main root, we see that 71 is greater than 50. So we put it at the right side of 50. Then we check 80. 80 is greater than 71. So it goes at the right child. 99 is greater than 80, so it goes to the right child of 80. And we continue with the same strategy until end of this BSD. We have three types of order. We have three types of order for a tree: pre-order, in order, and post order. This is just because of changing the place of root. In pre-order, first we have root. First we represent the root of BSD. After that we represent the left child of BSD. And then we represent the right child of BSD. In order, first we represent the left child of BSD, after that right child, after that root, and finally the right child. And in post order, first left child, then right child, and at the end, we represent the root. So in this tree, for pre-order, first we have for pre-order first we have 50 because the root should come first. After that, left child. So the left child will be a new BSD. The root comes first, so we put 30 at first. After that, again, left child will be the new root. So 25 will represent because the root comes first in pre-order. Then 1. When we reach to 1, we check whether it has a left child or not. It doesn't have left child, so we represent the right child. The right child is a new BSD with root 7, so we represent 7 and 5 because 5 is the last leaf, so we end this BSD. We don't continue this BSD anymore, and we go to the right child of 30. So after 5, we represent 40 as the right child of 30. Then we already finished this BSD. And we go to the right child of 50. The right child of 50 is here, so 70 1 as the root of this tree will be represent. After that, left child, it doesn't have left child. Then we go to right child of 71. The right child of 71 is another BST with root 80. So we represent 80, and after that doesn't have left child. We represent the right child, which is 99. In order, we have the same strategy, but the difference is first we represent the left child. After that, we represent the root, and after that, we represent the right child. So first we go to left child. The left child will be new BST. Then again we go to its left child because it has left child again. So this one also will be a new BST. Then again this one will be new BST. 175 will be new BST. And one doesn't have left child, so we represent 1 at the first element. After that, right child of 1. The right child of 1 is 7. We represent 7. We go to 7 as new BST. We represent 5 as its left child. After that, 7. Okay, I don't continue. I want you to think about it. Do you learn this one? Do you know how is the process of writing pre-order, in order, and post-order? Because I have an exercise for you. Everyone knows how we can represent pre-order, in order, and post-order. It's important. It's important to know its concept, because when you are going to implement it, you need to know the concept. Okay. I'm asking, did you get it? Did you understand it? Okay. Let's go to an exercise. Please don't come late, because I go to a slide and I cannot see your request for coming to the class. So please come before 9:10, because after that I cannot see your request. I go to a slide or 5. Still, I have a lot of students that I should give permission to come to the class. I'm doing Okay. Now I have an exercise for you. Okay. Please write in order, pre-order, and post-order for these three. For these three. Okay, let's see. Okay, I don't know what happened. I will fix it. Okay, can you see the tree now? Okay, the first three students that give the answer, they receive extra marks. So just start now. You write in order, pre-order, and post-order for these three. And also write your name. If your name is not determined in your account, so you can write your name as well. Okay, are you doing it? Okay, thank you. After that, I will share the link with you, then you can check whether your answer is correct or not. Okay, thank you. What about other students? Very good, thank you. This is the link. You can go and check your answer after class. Thank you so much. Now we go through the rest question. Thank you. Okay, in next question, we need to create the BSD node.java and we need to insert characters FACULT and Y into our BSD. After that, we need to print the number of elements of BSD, display BSD elements in pre-order, in order, and post-order. D, remove character L from BSD, and again display the new BSD. The example output is like this. So we can use the ready operations. When we want to show the size of a tree, a BSD, we use tree.getSize. We use tree.getSize. Easily we use this operation. After that, we need to show the pre-order of BSD. So we use bsd.preorder just to order the BSD based on pre-order. Just we are setting the order, not displaying. We are not displaying the tree using this one. Just we are setting the order pre-order. We are setting pre-order. After that, we show the tree using tree show tree. Then again, we want to set in order. So we use tree set order, BSD in order to set the order of in order for our BSD. After that, when we set this type of order, we show the tree. We display the tree. And finally, we set post order for the tree. And after setting tree as post order, then we show the tree, or we represent the tree using tree show tree. When we want to add node to BSD, we use add node. So here we want to add FACULTY to our tree, which is a string. So we use a string strlen in our loop to get all the characters one by one, to add all the characters to tree one by one. So first we add F, and after that, in second round of this loop, check whether A is smaller or greater than F. The ASCII code will be checked, and because it's less than F, we put A in the left child. Okay, and then we continue until we form our BSD. Then we can use display tree to show represents the whole tree. And we use tree remove to remove one character from tree, then automatically the tree will change to new form, and we display tree to see the new tree, the new BSD. And finally, we print out the tree. Okay, this question was easy. Let's go to do you have any question? Is it clear? Is it clear? This one? Okay, let's go to next question. In this question, we need to implement the operation by ourselves. So we need to implement get size, get height, add note in order, pre-order, post-order, and remove note. There are some points that we need to pay attention to them. The BSD has the maximum size of 20, and always the left child, if we have node K, if we have node K, the left child is 2K plus 1, and the right child of node K is 2K plus 2. And it's important, for example, if K is equal to 0, then the left child is position 1 and the right child is position 2. For pre-order, in order, and post-order, we use this strategy to represent the tree, the BSD, in form of in order, pre-order, and post-order. Let's go to answer. Okay, for isInt is a Boolean function like previous implementations that we have in Q, stack, previous data structure. It's a Boolean, and when the BSD is empty, the index should be assigned as -1. For getting size of the BSD, we need to use a loop. For this loop, we have max. If BSD is not equal to null, we add to count. The count is number of elements that we have in our BSD. And we continue this until end of BSD or until end of max. If we reach to max or if we reach to end of BSD, for example, if we have only 5 elements, after BSD 5, we reach to null, and then we break the loop. So the count will be 5. We use this one for getting size of BSD. That one was easy. For height, we use this formula. This formula is important. We use this formula to get the height of our BSD. Why? Because always we divide our BSD by 2 and we use log 2 to calculate the height of BSD. So this formula is important and you need to understand and you need to know why we use this formula to get the height of BSD. Okay, the next implementation is adding node. For adding node, we need to check whether the BSD is full or not because our BSD has a maximum, so we need to check the maximum. If we didn't exceed maximum, we can continue for adding elements to our BSD. And also we need to modify index. We need to modify the index when the BSD is empty and we are going to assign the first element. We assign index as 0 and we put T inside of BSD 0. And if it is not the first element and our BSD is not empty, we go through this while, we go through this loop. And then we check whether we reach to maximum or no. If we didn't reach to maximum, we continue adding elements to BSD. And when we add an element to BSD, we have a flag or we have a logical variable that we assign it as true. When we want to insert the root, we need to check whether the element, we need to check whether we should insert the element at the left side of the root or at the right side of the loop. So here we check. It's not easily adding an element. The adding element is more complex than previous data structure. In previous data structure, just we check whether we reach to maximum or no. If we didn't reach to maximum, we simply added an element. In previous data structure, it was like this, like a stack, like queue. But here, when we want to add a new node, we need to know whether it should be insert to left child or it should be insert to right child. So we assign the index of element, the index of new element based on the situation of the element, based on the amount of element, whether it's less than root or it's greater than root. And we have set order. For in order, post order, and pre order, we use set order procedure. Then how we implement them? We implement here, for example, for in order, we implement in order here. How we said for in order, first we need to represent the left child. After that, we need to represent the root. And finally, we need to represent the right child. As we said, for the left child, we had 2k plus 1. For the right child, we had 2k plus 2. So when we want to assign the index of left child, we use 2k plus 1. And when we assign the index of right child, we use 2k plus 2. So when we have in order, 2a plus 1 means that we have the left child as a new BSD. If we don't have any leaf for this BSD, for this new BSD, just we represent the root. And if we have again some leaf for this one, we go to leaf and we get the leaf as new BSD. So we have this order for in order. First left child, then root, and finally the right child. For pre-order, first we have root. First we display the root. After that, not displayed. First we assign the root. After that, the left child. And finally, the right child. So we order the BSD in this order. The left child will be represented using 2a plus 1 and the right child 2a plus 2. And the root will represent using the first statement. For post order, same as in order and pre-order, we check first whether the BSD is null or no. If it is not null, we go through BSD and first we represent the left child, after that right child, and at the end we represent the root. Okay. Now we can repeat what we had in question 2, but the difference is that now we have implemented all of the operations by ourselves. Pre-order, in order, and post order is implemented by us. So we repeat to see whether the output of our program is correct or not. Do you have any question for this one? Is it clear? Okay, like previous sessions, I will upload the answer of this tutorial in Spectrum. If I don't forget, I will do it by today. Is it clear for you? Do you have any question? Okay, thank you. I ask demos to start the lab part, lab session.
Morning, Doctor. And
Good morning.
yeah, so I just start with